In the chapter Normal Modes of Continuous System, till now we have discussed the two most important examples for calculating the normal modes of vibration. In the first example, we have seen the problem of transverse vibration of a string, and after that, we have discussed the longitudinal vibration of a rod. Now, this is the third and last example for discussing the normal modes in a continuous system. And here, as a continuous system, we are going to take an air column. So, today we are going to start to deal with the problem of finding normal modes of vibration of air columns, okay, or you can say gas columns. In fact, this is a very important problem because when you will discuss in next chapter the concept of wave, then there you will find the problem of Newton's formula for velocity of sound, the open organ pipe and the closed organ pipe. Actually, the basic ideas of those problems come from here. In fact, when you say vibrations of air column, here vibration means longitudinal vibration. You will see that an air column also vibrate longitudinally, not in transverse manner. Okay. So how we can discuss the problem of calculation of normal modes and normal frequencies in case of the longitudinal vibration of air columns, we will see now. In fact, again, just like the problem of longitudinal vibration of a rod, I have divided this concept in two parts. In the first part, we are going to see only to find the equation of motion, okay? And in the next lecture, we will see how to discuss the normal modes in case of this vibration of air columns, okay? Actually, I have divided this lecture in two parts for your convenience, because if I will try to cover up all the concept in one lecture, that will be a lengthy, that will be a time-taking process and a large video, which is not very interesting. Okay, so to keep the length of the video just feasible, just practical, I have divided this lecture in two parts. Okay, so now let us see how we can discuss the problem of vibration of air columns and how we can obtain the equation of motion. Actually, when you talk about air or any other gas, you know, this air or any other gas may be regarded as a continuous medium at ordinary pressure. Although in solid, the atoms of the solid or the particles of the solid are very closer with respect to the gas. But even after that, at ordinary pressure, we can treat the system of a gas or air as a continuous medium. In fact, why we can treat it as a continuous medium, you can see that if you consider 1 cubic centimeter of air, let us say there is an air whose volume is 1 centimeter cube, okay, 1 cm cube, and this is under the condition of normal pressure. Then it is found that this system contains almost 2.7 into 10 to the power 19 particles or molecules. So only the 1 centimeter cube volume of air or a gas at normal atmospheric pressure contains this much large number of molecules. You can see the number of molecules is enormously large. This is 2.7 into 10 to the power 19, and this large number of molecules is contained only in 1 centimeter cube volume. That's why the average distance between the molecules will be very small. The molecules of this gas will be very close to one another. Okay? And so, as an approximation, we imagine the number of molecules becoming infinite and the distance between them tending to zero. And this is the reason why we consider an air column as a continuous system. I think we have understand the logic why a gaseous system is treated like a continuous medium, because at ordinary pressure, that is at atmospheric pressure, the intermolecular separation is very small, it is almost zero, and so such a system may be treated as a continuous system. Okay? And so that we can handle this problem just like the problem of a string or the problem of a rod. Okay? So it is clear that a column of gas represents a system almost equivalent to a solid rod, almost equivalent. Just as in case of a solid rod, the medium was continuous, and when the rod was disturbed by exerting external longitudinal force, you have seen that the particles of the rod start vibrating in longitudinal manner. In the similar manner, you will see here, whenever a gas column will be disturbed, it will perform a longitudinal oscillation, just like the particles of a rod. So I have told you that this gaseous column represents just a system almost equivalent to a solid rod. In fact, both are continuous system and have internal elasticity. But there is a small difference. When you have discussed the problem of a solid rod, then the elasticity was Young's modulus of elasticity. Okay? But in case of this gaseous system, elasticity will play same role, but in case of gaseous system, you can't define Young's modulus of elasticity, but instead of Young's modulus of elasticity, in case of the gaseous system, the relevant modulus of elasticity is the bulk modulus or the volume modulus of elasticity. Okay? So instead of Y, in this problem, we will have B. B is the bulk modulus of elasticity and Y is the Young's modulus of elasticity. Okay? So this Young's modulus of elasticity will be just replaced by the bulk modulus of elasticity. And so this problem is just identical to the problem of longitudinal vibration of a solid rod. Okay? Now let us see how we can discuss this problem, and as I have told you in this first part of the lecture, our aim is only to obtain the equation of motion, not to discuss the normal modes of vibration. That will be the subject matter of our next lecture. And for this, let us consider a cylindrical tube. As you can see in this first figure, actually I have shown here a cylindrical tube. And we consider that this A is the cross-sectional area of this cylindrical tube, and this is a uniform cylinder. And this cylindrical tube is filled with gaseous system, or you can say air or gas is filled, is contained in this cylindrical tube. Okay? And we also assume that the gas which is contained in this cylindrical vessel, its density is rho. So rho is the density of the gas and A is the cross-sectional area of this cylindrical tube. Okay? As you have seen, in the case of problem of continuous system, we always divide the medium into a small elementary elements or slices. Just like that, here we will also divide the column of the gas into a small elements or a small slices. And we consider that each small element or slice has a length delta x. So this delta x is what? This is length of each element. As you can see in this first figure, I have shown actually the equilibrium state of the gas or the undisturbed state, when the gas column has not been disturbed, not been perturbed. Then I have shown in this figure one element or one slice lying between the section A and the section B. Okay, so AB is such an element, and you can see I have considered that this delta x represents the length of this element. In fact, this first figure represents the gaseous column in equilibrium state, when no disturbing or perturbing force has been applied on this column. Okay. So this first figure, as I have told you, represents the equilibrium state or the undisturbed state of the gaseous column, and AB, as you can see in this first figure, is the slice or element which you have considered. Okay. Now, if both of the ends of this cylinder is open, then you know the pressure exerted on this section A from outside will be just the atmospheric pressure. Okay. So this P naught is the pressure exerted on section A and section B, or you can say that this column is compressed by pressure P naught from both sides, which is simply the atmospheric pressure. In other words, you can say that P naught is the equilibrium pressure. Okay, P naught be the equilibrium pressure or the atmospheric pressure. Okay. Now, if you consider that the volume of this slice or element AB in undisturbed state, in equilibrium state, then what will be that volume? You can easily see volume is simply equal to area of cross section times length. Now, we have assumed that the area of cross section of this cylinder is A, okay, and length of this column AB in undisturbed state is delta x. So the volume of the element in undisturbed state will be V equal to A times delta x. Okay. Actually, I have written all these facts in brief for your convenience. So I will suggest you, when you watch the video, definitely open your pen and copy notebook and write down these things in your notebook, because when the video will be finished after a long time, you may forget these things. But when you will write these things in your notebook, definitely that will help you for in case of revision for your examination purpose. So definitely write down these things in your notebook. Okay. So till now we have talked about the undisturbed state of this gaseous column. But now let us see this figure number 2. Okay. Actually, we have to produce a vibration in this column, and for producing the vibration, you know, definitely this column must be disturbed. Okay. So the gas enclosed inside the element actually acts like a compressed spring, which would like to extend itself, since the gas exerts an outward pressure on the walls of the element. Okay. So now let us analyze the motion of the element of the gas when it is disturbed along x-axis. Actually, we treat this direction as x-axis, and we produce a disturbance or a perturbation along this x-axis, so that the gas contained in this column AB will be disturbed along the x-axis. How this gas can be disturbed? There may be several ways, several techniques to disturb this gaseous column. One of the most practical example you can take, if you have to disturb this gas, you can take a tuning fork and let us vibrate that tuning fork at one of the ends, let us say at the end A. And when the tuning fork vibrates at the open end of the tube containing the gas, then the particles of the gas at the section A move to the right, okay, to the position A dashed, as you can see. And it actually oscillates about A. And in the similar manner, the particles at section B also oscillate about B. So this is just a practical example to disturb the gas. You can vibrate a tuning fork at the open end of the tube, and due to this vibration, the air column will get compressed and the particles or the molecules of this gas at the section A will get displaced in rightward direction, but this will oscillate because a restoring force will act on it due to the elasticity. What will be that restoring force? We will just calculate for getting the equation of motion. Okay. Now, let us consider that in undisturbed state, the x coordinate of section A is x1. You can see the figure. Okay. So I have marked here x1 and here also x1. And the x coordinate of section B we have assumed is x2. Actually, these coordinates has been defined by taking the origin at an arbitrary position. You may take, let us say here there is origin, and with respect to this arbitrary origin, x1 is the x coordinate of section A and x2 is the x coordinate of section B. Okay. So in undisturbed state, can you say what will be the length of this column AB? You can easily see AB, which is the length of this column, that will be equal to x2 minus x1. And we have assumed that this x2 minus x1 is equal to delta x. This is delta x. Okay. So the length of the element AB is equal to delta x, which is actually equal to x2 minus x1, where x1 is the x coordinate of section A and x2 is the x coordinate of section B in the undisturbed state of our gaseous system. Okay. But as we disturb this gaseous system, for example by vibrating the tuning fork at one of its ends, open end, then what will happen? Actually, when the gaseous system is disturbed, you can see I have shown in this second figure that this plane A is shifted to A dashed, okay, and the plane B is shifted to B dashed. And we consider that this displacement of section A is given as y of x1. So what is this y of x1? This is actually the displacement of section A at any time t, okay, when the disturbance has been produced in this gaseous column. And similarly, this y of x2 is what? This is actually the displacement of section B. It means when B displaced to B dash, it suffers a displacement y of x2. So you can say that this A dashed, this is equal to y of x1, and B dashed, this equals y of x2. Okay. So you can now easily say what will be the x coordinate of the section A dashed. As you know, x coordinate of section A is x1 and A dashed is at a distance y of x1. So the x coordinate of this section A dashed will be x1 plus y of x1. It is a very simple idea. And similarly, the x coordinate of plane B dashed will be what? That will be x2 plus y of x2. Okay. Again, all these things which I have just explained, I have written here for your convenience. You can see, I have considered that the gas is disturbed along x-axis and the particles at the plane A move to the right and oscillate about A, and particles at B also oscillate about B. And what is this x1? This is x coordinate of section A, and x2 is the y coordinate of section B. And therefore, x2 minus x1, which I have assumed delta x, that is length of the element AB. Okay. And as I have told you, that second figure actually shows the disturbed state of our system, and we have assumed that y of x1 is the displacement of the particles at x1 and y of x2 is the displacement of the particles at x equal to x2. And therefore, x1 plus y of x1, this is x coordinate of A dashed, and x2 plus y of x2, this is x coordinate of B dashed. Okay. Actually, our aim is to find the net force acting on this element. And how we can find this net force? Actually, there are two techniques to find the net force acting on this column AB. First of all, by the idea of bulk modulus of elasticity, you can find the resultant force acting on this element AB. And after that, you may also calculate this net force using the well-known Newton's second law of motion. Okay? So let us first of all try to find the resultant force acting on the column AB when it gets disturbed. And for this, we consider that the section or the plane B, which is displaced by this y of x2, this displacement y of x2 is greater than y of x1. This is our assumption. You may take y of x1 is greater than y of x2. It is possible. But in this present calculation, I have assumed that the displacement of plane B is greater than that of plane A. So in this condition, as a whole, there will be an increase in length of the column of the gas, that is increase in length of this element AB. And when length will be increased, definitely as cross-sectional area remains constant but length increases, so definitely volume of this element will also increase. So after finding the value of increase in volume, we will be able to find the volume strain, and after getting the value of volume strain, we will be able to find what will be the excess pressure acting on this element. As you can see, I have considered in the disturbed state, the pressure acting on section A dash is P of x1 and that on section B dash is P of x2. Okay. And you can see the direction along which these pressures are acting. Okay. So now let us see what will be the increase in volume of the element AB. If you denote the increase in volume by the symbol delta V, what will be this? You know, this increase in volume will be simply equal to area of cross section times increase in length, because volume is area of cross section into length. But here area of cross section remains constant but length increases. So when you will multiply the area of cross section of the cylinder by increase in length of that element, then you will get the increase in volume of that element. Okay. And as you know, area of cross section we have assumed earlier, this is equal to A. And what will be the increase in length? Since this section A is displaced by y of x1, okay, and this section B is displaced by y of x2, and y of x2 is greater than y of x1. So when you will subtract this y of x1 from y of x2, you will get the increase in length or change in length. Okay, so change in length or increase in length is equal to y of x2 minus y of x1. How we can find the value of y of x2 minus y of x1? Actually, in my previous two videos on vibration of a string and also on vibration of the rod, you have used Taylor's expansion in first approximation for finding the value of y of x2 minus y of x1. So here I am not repeating the same thing. You can see my previous videos where I have discussed in very detail by using Taylor's expansion how we can find this y of x2 minus y of x1. And you have seen when we actually assume that this delta x is very small, it tends towards 0. In this limiting condition, you have seen that y of x2 minus y of x1 is simply equal to del y by del x times delta x. So I have written it here directly, but for proof you may watch my previous videos. Okay. So the change in volume or increase in volume of this element, which we have denoted by the symbol delta V, what is that? That you have obtained, this is A times del y by del x times delta x. Okay. So in this way we have calculated the increase in volume. Now, after getting the value of increase in volume, when you will divide this increase in volume or change in volume of the element by its original volume, what you will get? You know, change in volume divided by original volume, what is that? That is actually called volume strain. So now you can easily find the value of volume strain. You can see this will be delta V over V. Okay. So volume strain is given by delta V over V. But just you have calculated that this delta V is equal to this much. This is A times del y by del x times delta x. Okay. And the original volume we have calculated earlier, this is A times delta x. So this A and delta x will cancel out, and you can see that this volume strain is simply equal to del y by del x. So actually volume strain is the partial derivative of y with respect to. This is a very interesting result, most interesting and most important result. Actually volume strain is simply equal to slope of the curve y of x. This is a most remarkable result. Now volume in this case increases, but can you say why you say that volume of the element has been increased? Definitely, you know, in case of gas, when the volume of the element will increase, definitely its pressure will decrease. On decreasing pressure, volume will increase. So if you consider that delta P is the decrease in pressure of the gas after disturbing it, then what will be the pressure acting on the plane A when you disturb this system? You can see on the plane A I have shown that this pressure is P of x1, and when the gas was not disturbed, then pressure was P naught. So this P of x1 will be what? When you will subtract the decrease in pressure delta P from the initial value of pressure P naught, then you will get P of x1. Okay, so you can say that this P of x1, which is the pressure acting at A dashed, okay, that will be equal to P naught minus delta P. Okay, and similarly you have seen in that figure that we have assumed that P of x2 is the pressure acting on at B dashed. Okay, now delta P, as I have told you, this is decrease in pressure at A, and so you know the decrease in pressure or increase in pressure, this is the measure of bulk stress. I hope you have a concrete knowledge of elasticity because it is to study in your lower classes. So if delta P represents the change in pressure, this change in pressure is what? This is simply the measure of bulk stress. This is the measure of bulk stress. And that's why we can now define the bulk modulus of elasticity of this gas. If you denote the bulk modulus of elasticity of the gas by the symbol this capital B, how it is defined? You know from Hooke's law that this B is equal to volume stress or bulk stress divided by volume strain or bulk strain. But as you know, volume stress is nothing, this is simply the change in pressure. Okay, so this will be simply equal to delta P. And volume strain, you know, this is change in volume by original volume. But you know, when this pressure decreases, when delta P decreases, it means delta P is negative, then volume increases. So when delta P is negative, then delta V is positive. Okay. So if we do not use here a minus sign, then this bulk modulus will be negative. But bulk modulus is never negative, it is always positive. So for getting the positive value of bulk modulus, you must put here a negative sign. Whenever bulk modulus of elasticity is defined, we always put here minus sign. Why? Because in this case, definitely whenever delta P will be positive, then delta V will be negative. And when delta P is negative, delta V will be positive. So if we do not use here minus sign, then B will be negative, which is wrong, which is incorrect. For getting the positive value of B, you must take here minus sign. So you can say that this minus sign simply implies that whenever pressure increases, volume decreases. Or whenever pressure decreases, volume increases. Okay? As we have considered in the present case. And so now you can easily find what will be the increase in pressure, that is delta P. That will be simply minus B times delta V by V. But just now in this equation 2 you have obtained that this volume strain delta V by V is simply equal to del Y by del X. So this decrease in pressure delta P is given as minus B times del Y by del X. So in this way we have obtained the value of delta P, that is decrease in pressure in terms of bulk modulus of the gas. Bulk modulus of the gas. Okay. Now after getting the value of decrease in pressure, now we can easily find what will be the net force acting on this element. This is your element. Okay. And you have seen that if your aim is to find the net force, you have to find first of all what will be the difference of pressure in both sides. Okay. As you can see, I have assumed that at section B dash pressure acting is P of x2, and that at A dash the pressure acting is P of x1. Okay. So actually the pressure difference across this element A dash B dash, what will be this pressure difference? This pressure difference, will be equal to P of x2 minus P of x1. P of x2 minus P of x1. But again, if I will ask you how you can find the value of P of x2 minus P of x1, remember, just we have obtained the value of y of x2 minus y of x1 utilizing Taylor's expansion. In the same way, using Taylor's expansion, you can find it. But again, I am not writing the whole expression for Taylor's expansion because you have learned this thing earlier in several times. So on the basis of Taylor's expansion, particularly in first approximation, when you consider that this delta x is very small, then P of x2 minus P of x1 is equal to this much. This is del P of x by del x times delta x. Okay? But what is this P of x? This is actually P of x means P1 of x, which is P naught minus delta P. Okay? So this can be written as del x P naught minus delta P times delta x. But P naught is the equilibrium pressure acting on the end A, which is just equal to atmospheric pressure in our present situation. So it is constant. And therefore, del P naught by del x will be 0. And if it is 0, our expression is minus del x delta P times delta x. Okay? But you have just obtained the value of this delta P in equation 3. So let us substitute the value of delta P from equation 3 here, and then you will get that this P of x2 minus P of x1, which is actually called excess pressure, that is equal to minus del x minus B times del y by del x times delta x. Okay? Here actually B is constant, so it will be outside of the operator, and when this del x will be operated on del y by del x, this will be del 2y by del x square. And this minus times minus will become plus. Okay? So the excess pressure acting on the element AB is given as B times delta x times del 2y by del x square. So in this way, we have obtained the excess pressure acting on this. And if we will multiply this excess pressure by the area of cross section, you will get the net force acting on this element. So the net force acting on this element, if you assume it as F, that F will be simply equal to cross-sectional area of the element times excess pressure. Okay? This is just the definition of pressure. Okay? So F will be equal to what? Cross-sectional area, you have taken it as A, and excess pressure you have just calculated here. This is B times delta x times del 2y by del x square. So you can see how we have obtained the resultant force acting on this column of air or gas by the concept of elasticity. Okay? Now, as I have told you earlier, again we are going to find the same force but by another method. And for finding its value by another method, you can think about Newton's second law of motion. In accordance with Newton's second law of motion, the net force acting on a system is simply equal to mass of the system times its acceleration. Okay? So now see, what will be the mass of this element? Mass, this is simply equal to density times volume. And you have assumed earlier that density of this gaseous system is rho. And what is the volume of this element? You have seen this is A times delta x. A is area of cross section and delta x is length of the column. So A times delta x is what? This is volume of the element. So rho A times delta x, this is the mass of that element. Now in x direction, our element suffers a displacement y. So y is its longitudinal displacement. And when you will take the second order derivative of this y with respect to time t, you will get its acceleration. Again, here you can think that this y is not only a function of t, but along with t, it is also x dependent. It is also a function of x. So I have taken here partial derivative, del 2y by del t square. So finally, applying the Newton's second law of motion, we obtain the net force acting on this element is given by rho times A times delta x times del 2y by del t square. So now you can see the net force acting on the element has been obtained by applying Newton's second law of motion in this equation 5, and we have obtained the same force acting on the element by using the idea of a bulk modulus of elasticity in this equation 4. Okay. So now we can equate the two forces. Okay, and after equating the two forces, we will get the equation of motion of the element of the gas. Okay. So now let us equate these two equations, 4 and 5. You can see in accordance with equation 5, F is this much, rho A delta x times del 2y by del t square. And you have seen in equation 4 that same force is given by AB times delta x times del 2y by del x square. Now you can see that this A and delta x will cancel out, and therefore del 2y by del t square, this will be equal to B over rho times del 2y by del x square. And instead of this B over rho, we have written here V square. Actually, this is the equation of motion of the element. Here V is a constant because for a given gas, the density will be constant if you treat it as an incompressible fluid, and B is the bulk modulus of elasticity, which is also a constant. Okay. And again, I am reminding you, you have already studied the differential equation of a one-dimensional wave. And when you will see this equation A1, you must recognize it. This is nothing. This is simply the famous classical wave equation in one dimension. So actually the equation of motion of this element represents the classical wave equation. But here, as I have told you several times, our aim is not to discuss the wave generated in this air column, but our aim is only to discuss its vibration, not its wave aspect. But when we will see that the wave theory, the result will be same, and then we will say that actually in this case, in this air column, a sound wave which is a longitudinal wave travels in this air column. So in air, sound wave is a longitudinal wave, and during this vibration, sound wave actually travels. But here we will not say this. Okay. In fact, you will see that this V, which is equal to a square root of B over rho. You must remember this. This is a most important result when we will discuss the velocity of sound wave in air and Newton's formula and Laplace correction. then you will see I will write this expression directly. What will be the value of B that was obtained by Newton, which was incorrect, and finally Laplace has found the value of B for a gas in correct form. Okay, that we will study in our next chapter. Okay. But here you can see, if you will find the dimensions of this constant V, you will get that its dimensions are simply the dimensions of velocity. Okay. So so that in wave theory this is called wave velocity of the wave or phase velocity of the wave. Let us see. You know, dimension of elasticity, this is ml inverse T inverse 2. Okay. And dimension of density, you know, these are ml inverse 3. And here there is a square root, so I have taken here a square. And you can see, after simplifying it, the dimensions of this constant V is LT inverse. But you know, LT inverse, these are the dimensions of velocity. Okay. So the constant V has dimensions of velocity. And these are the two most important results which I have mentioned in equation A2 and A1. And A1 is the equation of motion of this air column. Okay. As I have told you that the aim of our present lecture was only to obtain this equation of motion. But the basic problem which we have to discuss is what? That is the discussion of normal modes in this case. And that is the subject matter of our forthcoming video. Okay. Thank you very much.